This lecture is in electronics. Today we will discuss the DC biasing of Bjt transistor. First, we want to know what's the meaning of biasing. Biasing is applying an external DC voltage to the device or to the transistor in order to turn it on and place it in the operation in the region of characteristics where the device operates most linearly. So, because the aim of the biasing is to achieve a certain condition of current and voltage, this specific value of current and voltage, we will call it the operating point, or we can call it a quiescent point, and as abbreviation we call it the Q point. So the operating regions for the transistor output characteristic curve, as we can see, there is three operating regions: the linear region, the cutoff region, and the saturation. The most important region that the transistor behaves or active or operates linearly is the linear region operation, where the base emitter will be forward biased and the base collector will be reverse biased. As we can see, there is a limit for this region, and we mean it the linear region. This limits we can see it, it's the I maximum and V maximum. So this is the maximum limits for operation of transistor in the linear region. So after these values, the transistor will operate in another region. Now we come to the circuit types of biasing of DC transistor. We take the first circuit type. We call it the fixed bias circuit, as we can show in the figure below. It provides a straightforward and simple starting point in the DC bias considerations. As we can see, here we have an NPN transistor and a collector resistor and a base resistor and a power supply, DC power supply. We call it the VCC, connected to both the collector and base. The analysis of this circuit will divide it into two main parts. The first part is the loop of the input circuit, and we mean by the input circuit the circuit between the common branch and the input branch. So we can also call it the base emitter loop. To identify the voltages in this loop, we will use the Kirchhoff voltage law, so we can analyze or calculate the voltages in this loop. As we can see, this is the base emitter loop. We will start with VCC and ends with the ground. The loop will be as follows: that VCC minus VB, which is equal to IBRB, minus the base emitter voltage equals to 0. And from this mathematical formula we can conclude the value of base current, which equals the VCC minus VBE divided by the RB. So after we finish the base emitter loop, now we will come to the base collector or reverse bias of the base collector loop. So we can see, as it is in the figure, as it's shown in the figure, we will begin also from the VCC and applying the Kirchhoff voltage law. VCC minus the ICRC minus VCE equals to 0, and from this mathematical formula we will be able to calculate the collector emitter voltage, which is equals to the VCC, the power supply, minus the IC dot RC. We can take advantage of the base current we calculated from the input loop as we can see, and calculating the collector current by using the formula that says that the collector current equal to the base current multiplied by beta. Now we will have a simple example for this circuit, the fixed bias circuit. The example says compute the DC bias voltages and currents for the circuit shown in the figure. This is the fixed bias transistor circuit. We have the VCC equal to 12 volt, RC 2.2 kilo ohm, RB 240 kilo ohm, and the beta equals to 50. Now first, from taking the base emitter loop, we will calculate the IB, which is equals to the external power supply minus the base emitter voltage divided by the base resistor, and applying the mathematical numbers, so we can conclude that the IB equals to 47.08 microampere from the base current. And because we have the beta, we will be able to calculate the collector current, which is equal to 2.35 milliampere. And there is another example for the fixed bias circuit. As we can see, we want to compute the collector voltage and current from the circuit of the figure. So we, in the same method, in the same procedure, we will be able to calculate the base current, then the collector current, and the collector emitter voltage, and which is equals here to the collector voltage. Now we come to the other circuit type, which is called the DC bias circuit with emitter resistor. This circuit differs from the fixed bias circuit, that we will have a resistor in the emitter branch, as it is obviously here. So the analysis will be the same. We will take the base emitter loop, and then we will take the collector emitter. We first come to the base emitter loop, and applying the Kirchhoff voltage law, we will have the VCC minus the VB, which equals to IBRB, minus the base emitter voltage minus the emitter voltage, which is equal to the RE dot IE. And we can find here that we have two current terms. We have the IB and we have the emitter current. And because there is a relationship between the emitter and base current, we will take advantage of this relationship, which is equals that the emitter current equals to the collector plus base current, and so it equals to the beta plus 1 multiplied by base current. We will use this formula and use it in the Kirchhoff voltage law, and so that we can have the IB equals to VCC minus VBE divided by RB plus beta plus 1 RE. We finish the base emitter loop. Now we come to the collector emitter loop, and the same, we will take the Kirchhoff. By applying the Kirchhoff voltage law, we can have the VCC minus ICRC minus VCE minus IERE equals to 0, and from this formula we will be able to calculate the collector emitter voltage. So the collector emitter voltage equals to VCC minus IC multiplied by RC plus RE. The emitter voltage and collector voltage also will be calculated from this formula. We will take example for this circuit type. Calculate the bias voltage VCE and current IC in the circuit of the figure. And we have the parameters that the RC equals to 2 kilo ohm, the VCC equals to 20 volts, RB equals to 403.30 kilo ohm, and RE equals to 1 kilo ohm, giving a beta equals to 100. We will apply the mathematical formulas, so we obtain that the IB equals to 36.35 microampere. Multiply the IB by the beta, we will conclude, or we will obtain the collector current, which equals to 3.635 milliampere. And so we can obtain from the output loop the collector emitter voltage, as we can see in the mathematical formula. So it will be 9.1 volt.